Hi and welcome back. Thank you for joining today. Vec is a data structure that we all know and love, and I'm extremely excited to explain it to you the best I can. We return to the same code as the beginning and end of the last video. This is the source code of Vec from the Rust standard library. Like before, a lot of this code's purpose is versioning information for APIs. I won't be including most code like this for the rest of the video. If you want to see any code in this video in its full, unedited glory, I'll put a link in the description. It's all open source. Let us begin. Last time, I explained that this bound, a allocator equals global, controls the allocation behavior of a vec. For a more in-depth explanation, I'd highly suggest watching my last video. Shameless self-promotion. Now that we've covered the allocator trait, we can cover vec itself. To start, let's see how the vec struct looks in memory. We can visualize vec's memory layout using a sequence of boxes, each box representing 1 byte or 8 bits. According to the source code, vec is made up of 2 fields, buff and len. Buff is a RawVec with the same type parameters as the outer vec, and len is a usize. We'll assume that we're on a 32-bit system, which means that all memory can be addressed by a 32-bit pointer. On a 32-bit system, usize is 32 bits or 4 bytes. We can see that vec has 2 parts, a RawVec and a usize. We will build up an intuition for these parts as we dive deeper into the code that defines vec. So that's what a vec looks like. What parts compose a RawVec? RawVec is a struct with the same type constraints as vec. Pub crate means RawVec is visible within the current crate. Crate is library in Rust speak. The underscore marker field is a phantom data to t. The underscore at the beginning of marker is a naming convention to indicate that it's an unused field. What is phantom data? Sounds spooky. Phantom data is a marker trait that indicates that a type owns its data. It is a zero-size type or ZST, which means that it doesn't actually take up space in memory. Since RawVec doesn't have a field that uses the t type, there has to be a phantom data to t so the compiler knows how to drop the RawVec's data. Cliff L. Biffle, amazing name, has a great blog post on this topic that I'll link in the description. The underscore marker field, then, doesn't contribute to the memory profile of RawVec. Let's revise the vec memory layout from before. So far, we know that vec is a RawVec and a usize. RawVec has 2 fields, inner and underscore marker. Underscore marker is a zero-sized phantom data, and inner is a RawVec inner. So RawVec TA becomes RawVec inner A. Now that we know the internals of RawVec, let's see the internals of RawVec inner. Notice that RawVec inner is only parameterized over A. RawVec inner's only type parameter is A allocator. This means that it is type agnostic over T. Remember, that's why RawVec needed a phantom data. Since Rust does static dispatch, ditching the T parameter for the most fundamental vec operations saves on code gen and enables smaller binaries. Large binaries have been a complaint against Rust, and it's clear that the standard lib authors are doing everything to improve that aspect of the language. This safety guarantee will come into play later. For now, we'll ignore it. Back to the memory layout. So far, we have a RawVec inner and a usize. RawVec inner has 3 fields, pointer, cap, and alloc. Pointer is a unique pointer to a U8. Cap is a cap, and alloc is an allocator. We know from the previous video that the global allocator is a ZST, so the alloc field, like underscore marker, doesn't use any memory. Thus, RawVec inner becomes a unique pointer to U8 and a cap. Now that we've mapped out RawVec inner in memory, let's discover what a unique pointer to U8 is. According to the docs, a unique pointer is a wrapper around a raw non-null star mute t that indicates that the possessor of this wrapper owns the referent. In other words, this struct acts as a non-null mutable pointer that behaves like the type being pointed to. Basically, it's a mutable pointer that's guaranteed to be valid and the sole owner of its data. Repr transparent means that unique is guaranteed to be identical in memory to its inner field. A transparent struct must have at most 1 non-ZST field. Unique satisfies this constraint with non-null. Similar to RawVec, underscore marker is a phantom data which marks that unique owns its underlying data. So a unique pointer to some type T would own that T and enable certain drop behaviors and semantic rules on unique. The authors left a comment pointing us to an explanation of why unique needs this phantom data marker. I'll leave this RFC link in the description. Let's get back to the memory visualization. So we have a unique pointer to U8 with two fields, pointer and underscore marker. Pointer is a non-null pointer to T, and underscore marker is a phantom data to T. Remember, phantom data is a ZST, so it doesn't allocate memory. Since unique is transparent, we can replace unique U8 with non-null U8 because they have the same memory layout. So unique is a non-null mutable pointer. What is non-null? As we saw in the last video, non-null is simply a wrapper for a raw immutable pointer. The struct ensures that its internal pointer is always non-null, so the compiler can consider it a guarantee and make optimizations on the assumption that the pointer is indeed non-null. Similarly to unique, the struct is also wrapper transparent, so it'll look identical in memory to a const pointer. The biggest difference between non-null and unique is that unique owns the data and non-null doesn't. Since unique owns its data, it's allowed to mutate it. Non-null, on the other hand, can't mutate its data without upgrading to a unique pointer. That's an oversimplification of borrowing rules. Go read the Rust book if you haven't. So in the memory layout, we can continue our drilling. A non-null pointer to U8 has one field, pointer, an immutable raw pointer to T, pronounced *const T. So we can replace non-null U8 with *const U8, a pointer to an unsigned 8-bit integer. Since pointers are memory addresses and memory addresses are numbers, all pointers are simply a usize. We've now almost constructed the entirety of Vec using only built-in types. So we have a non-null pointer inside of a unique pointer inside of RawVec inner pointing to a U8. Lastly, we have cap. All we need to know about cap for right now is that it's a transparent wrapper around a usize. We'll understand more about its specifics later. There's still plenty of video left. Since cap is just a usize, we can replace cap with usize. So now we just have three usize values which represent the entire structure of Vec. Let's zoom back out past cap. Out from RawVec inner, out from RawVec, and back to Vec. Like all memory, Vec is a sequence of bytes. Specifically, Vec comprises three usizes, a pointer, a capacity, and a length. That's it. The pointer points to the beginning of the Vec in memory. The capacity is how many memory positions are allocated to the Vec, and the length is how many elements are actually in the Vec. And that's the memory layout of Vec. So we've seen the structure of Vec. Next, we'll see how this code manipulates the Vec to do a bunch of stuff, such as pushing to the Vec, creating a Vec with a specific capacity, using a macro to construct a Vec with literals, indexing into a Vec with either a number or a range, and lastly, how Vec is formatted to be displayed on the console. However, I'm saving most of that for future videos because it's simply too much to talk about in one. So for now, welcome to episode 1 of how Vec works in Rust. Was that a good cold open? Was it too long? Too bad, this is my video and I do what I want. Get your popcorn, we are just getting started. We begin by constructing a Vec called v1 using the Vec new associated method. Vec new is called an associated method because it doesn't need an instance of Vec to exist yet. Here, Vec new is a constructor for a new empty Vec. The compiler is helping us do some work here though. Since we immediately push integers onto the Vec, the compiler infers its type. In a way, the code we're seeing is just syntax sugar for this, where the type of v1 is explicitly labeled as Vec i32. Knowing that, let's find out how Vec new works to create a Vec with the structure we explored before. Vec new is a public const method. Const means that the method can be called at compile time, which means its result will be pre-computed for the user during compilation. It returns a self, so it returns a vec t. We know that self is vec t because of the surrounding impl block. Be sure to check the implementing type if you're unsure what self means throughout the video. Don't forget this tip. I'm not going to say it again, and some of these method signatures are daunting. Inline is an attribute. It hints that the contents of the methods should be inserted into the calling function rather than inserting a jump. When the CPU jumps from one function to another, it typically has to call up that function's memory. But if the contents of the function are already there, the CPU can quickly fetch them, which can be more efficient. However, this leads to bigger binaries because of extra code gen, so inline should be used on small and crucial functions, perfect for vec new. Must use triggers a warning if the user doesn't do something with the return value, like assigning it to a variable or passing it to a function. The function body itself constructs a vec with a length of 0 and a new RawVec for buff. Let's see how RawVec new creates a new RawVec. As expected, the method takes nothing and returns self, aka RawVec. Notice that we're implementing a RawVec with a global parameter. Thus, this new method only exists on a RawVec using the global allocator we discussed in the last video. Global is the default allocator used by Rust standard collections. It is a ZST that implements Rust's default allocation behavior. So we're working with a RawVec using the global allocator. The body of new simply calls a different RawVec method called newIn. It takes one parameter. We pass in global. Why does the newIn method need access to the global allocator? Let's see. The method takes in an a, which has to be an allocator, and returns a RawVec like the last method. The reason the new method calls the newIn method is to make vec easier to use. The end user never has to interact with the allocator API, and code reuse purists are throwing a party. The method body itself constructs a RawVec with _marker as a phantom data. The type of phantom data is inferred by the compiler. The inner field is a new RawVec inner made using the newIn method. This method takes two parameters, alloc and a line of t. Let's start from the inside out and see what a line of does. A line of returns a usize. According to the docs, this function returns the minimum alignment of a type in bytes. This is important. Every sized type in Rust has a size and an alignment. This function simply gets the alignment of the type t and returns it to the user. Rust C promotable is for const promotion. It has to do with extending the lifetimes of references, but honestly, I don't quite fully understand it, so I'll leave a link in the description of an explanation I found if that interests you. The function body calls an intrinsic function called min_align_of. This function does exactly what the last function does, but this version is a compiler intrinsic. That's what these attributes mean. Rust C no unwind signals to the compiler that this intrinsic never unwinds. Unwinding has to do with memory cleanup when a program panics. I'll link an explanation of this too, because it's another difficult concept. Rust C intrinsic and Rust C intrinsic must be overridden signal to the compiler that the function is an intrinsic and must be overridden. We can see that this version of the function is unreachable, so the compiler will insert the necessary code at compile time. User Sodibu left a great correction of my explanation of intrinsics in the comments of the last video, so I wanted to include it here. They say that what it means to be an intrinsic is that this operation is so fundamental it cannot be expressed in terms of other Rust code, either because Rust simply has no syntax to do that operation otherwise, or because there is some optimization, SIMD, that is impossible to implement in normal Rust without nicely asking the compiler to do it for you. Thanks for the explanation, Sodibu. So min_align_of is an intrinsic that gives us the align of the type t. It's called by align_of, which is just a wrapper for the intrinsic. Now we have the alignment of t. As we saw earlier, t is i32, and the align of i32 is 4. So we are passing in 4 as the alignment value for the RawVec inner newIn. Let's see how newIn creates a RawVec inner. The method, as we know, takes in an allocator a, alloc, and a usize align. The method returns itself, a RawVec inner. First, we create a pointer variable to be used inside of the constructor. We do this by using an unsafe transmute operation. Don't be nervous. Unsafe simply means that the compiler can't guarantee its usual safety when using this function. Instead, the programmer has to uphold a set of rules, a contract. Upholding an unsafe contract helps prevent you from encountering undefined behavior. Scary! So we use this transmute on our align value. Let's see how this unsafe function operates. Transmute is another Rust intrinsic, indicated by these attributes. The first attribute has a pretty funny history though. It was added as an override because the function was accidentally stabilized. Seemingly, in September 2024, the Rust team decided to move some of these intrinsics after stabilizing the ones in this location, so they had to make a workaround to allow them through unstable modules. I'll link the information in the description. The other three attributes are the same as we talked about before. Transmute itself is a very interesting intrinsic. It makes the compiler reinterpret the bits of one type as another type without changing the underlying memory. So it snaps its fingers and magically makes one type into another. You can imagine why this operation is unsafe. Here, we transmute a line, a usize, into another type. What type? Remember that RawVec inner's pointer field is a unique pointer to U8, which is transparently identical to *const U8. So we want to turn a usize into a unique pointer to U8. While we were talking, the compiler already had this figured out using its strong type inference system. This transmute is just syntax sugar for this transmute. So we're turning a usize into a unique pointer to U8. The safety of this operation is guaranteed because all usize bit patterns are valid pointers. This means that we get a pointer to the memory address represented by a line and bind it to the pointer variable name. Next, we construct a RawVec inner using pointer, alloc, and this cap0. Cap0 creates a cap with an internal value of 0. Why is this operation unsafe, you might ask? Well, the surrounding details of cap can help us explain. The cap new constructor has a comment describing the safety constraints of cap. It must be less than or equal to isize max. The valid range of a vec's capacity is 0 to isize max, but the type of capacity is usize, so the constructor ensures that this rule is always enforced by the user. Take note of this restriction of cap. It comes into play later. This restriction is hinted at further by these configuration attributes, which act as compilation guards. Basically, based on your operating system, 16, 32, or 64 bits, these configuration attributes act as hints to the compiler that the cap will never exceed isize max. This enables some extra compiler optimizations. So cap0 is simply a capacity of 0. Thus, we make the cap 0 for our created RawVec inner. Now, the RawVec inner consists of a unique aligned pointer, a capacity of 0, and a ZST allocator. So RawVec inner new in created our RawVec inner that lives in our RawVec, created by RawVec new in that was called by RawVec new that lives in our vec, created by vec new. Whew! We've now created a new empty vec i32 and bound it to the name v1. This variable now represents a vec in memory. As we saw before, vec consists of 3 usize values. In our case, pointer is 4, cap is 0, and len is 0. These 3 numbers in memory will be all we need to manipulate our vec's memory and perform our push operations. Finally, we've created our vec. Notice that we marked v1 as mute to enable mutation. Now the hard part. Let's see how the push operation uses our vec to create a sequence of numbers. This takes pretty much the rest of the video. Prepare. We begin with the push method signature. Push takes a mutable reference to the vec and a value t. The method has no return type because its intention is only to mutate the vec by adding a new element. It doesn't have to return any information to the caller. This attribute means that push is only enabled if global OOM, out of memory, handling is enabled. The standard allocator for Rust, global, simply panics if there's a memory error. For some allocators, memory errors are handled differently, so this push method wouldn't be valid. Thus, it can only be compiled when global OOM handling is on. Global OOM handling is enabled by default in Rust, so we typically don't have to worry about this. The rustc confusables attribute tells the compiler that this method name is often confused with other names. For example, if the user writes v1.pushBack instead of push, the compiler can hint that they may have intended to use the push method instead. The trackCaller attribute controls panic signaling. When a panic happens in the push method, without this attribute, the compiler would signal to the user that a panic happened in the standard library, and then the user wouldn't know where in their code that the panic happened. With this attribute, the compiler will say that the panic happened at the call site of push instead of the panic location. Now, the user will know exactly which line of their code caused a panic. Alright, back to push. Remember that it takes a mutable reference to Vec and a value t. The method is intended to append an element onto the Vec, mutating it in place. First, we set the len variable to the Vec's len. According to this comment, we do this to inform CodeGen that the length doesn't change across grow1. Basically, this tells the compiler that self.len only needs to be loaded once, because it won't be changed until after this call to grow1. So now we have the len as a variable. Next, we check if the length is equal to the capacity. If the length is equal to the capacity, that means that the Vec is full, and more space needs to be allocated. We will see how this behavior is handled in grow1, but first, the Vec's capacity is retrieved via this call to self.buff.capacity. Remember that buff is the RawVec field of Vec. So we call capacity, which takes a reference to self and returns a usize. The body of this method calls another method, self.inner.capacity, where inner is the RawVec inner field of RawVec. We call this capacity method with a single parameter, size of t. What does this size of t function do? Size of t takes a type t and returns its size. Remember from earlier? Every sized type in Rust has both a size and an alignment. This function takes the type t and returns its size. It does this by calling an inner function with the same name. This function is a compiler intrinsic, just like we saw before with min-align of. We know that because of these attributes and its unreachable body. So the compiler inserts the size of the type, which we get by using the size of t function. We put t's size into the self.inner.capacity method. Finally, we can see how this method gets us the capacity of the Vec. The RawVec inner capacity method takes a reference to self and the lm size we provided. If the provided size is 0, say we're working with a ZST, the capacity is usize max. Otherwise, the capacity we constructed earlier in cap is returned. Remember that this cap can't be more than isize max. So we've got the capacity that we called in RawVec's capacity method, and we compare it with the length of the Vec. If they're the same, we call the RawVec grow1 method. This comment explains that if we would allocate greater than isize max bytes, or if we've somehow pushed usize max plus 1 ZSTs into the Vec, the method will panic. We will explain this further as we dive into the implementation of the grow1 method. Get ready, this method is bulky. Most of our time today will be spent here. The method signature is simple. It takes a mutable reference to self and returns nothing. Like capacity, the body of grow1 just calls a method on inner with the same name. However, this method takes a parameter, tLayout. The all caps name lets us know that this is an associated constant. Let's see how it's defined. Hold on, this definition is cluttered with other information. This comment documents the isZST constant, which we won't encounter in this presentation. It pretty much does exactly what you'd expect. If t is a ZST, it's true. Otherwise, it's false. These two constants live in a trait called sized type properties. Sized type properties is implemented for all t, which means that every type in Rust has access to both of these associated constants. Except, I'm kind of lying. Not every type has access to these constants. Only sized types. This is a trait bound on a trait, meaning that any type that implements sized type properties must also implement sized. Sized is a marker trait indicating that a type has a size known at compile time. Types like i32 and an array of 4u8 have a size that we can know before the program runs. However, a type like slice of u8 can't be sized before the program runs, so it doesn't implement sized. Most types in Rust implement sized, including ZSTs. Their size is 0. Now I'm going to speedrun these attributes. The diagnostic attribute controls diagnostic messaging during compilation. The provided message will show up when attempting to use a type that doesn't implement sized in a sized way. The fundamental attribute gives the size trait special properties that enable it to be blanket implemented for all types T. This attribute also relaxes Rust's orphan rule, something something coherence rules, complicated trait theory, something. This attribute has to do with specialization, which is unstable. Sized can't be implemented manually on a type anyway, so this doesn't impose limits on the user. This attribute prevents users from implementing the trait. This attribute marks the trait as co-inductive, which changes how the trait solver treats it. A co-inductive trait can refer to itself recursively without breaking the compiler. I'll leave links in the description explaining all of these attributes in more depth because they're very complicated and interesting, but I think the full extent of their workings is beyond the scope of this video. This has been Attribute Speedrun. Sized is empty because it's just a marker trait. Its implementation is handled by the compiler. So sized specifies that a type has a compile time size. Sized is a trait bound on size type properties, which gives us the layout associated constant. What is layout? We discussed layout at length in the last video, but pretty much it's a combination of a size and an alignment, which all sized types in Rust have. Size is a usize, and align is an alignment. Watch the last video for an in-depth exploration of alignment. TLDR, alignment is just a usize power of 2, so only one bit is set. We'll see more about this later, so keep it in your mind. One more time, say it with me now. All sized types in Rust have a size and an alignment. We construct this layout using the new method. This method creates a layout for the generic type T. It starts by getting both the size and align of T using the sizeAlign function. This function gets both the size and alignment of T and returns them as a tuple of two usize values. This function has a pretty interesting history in the Rust compiler because it's outdated and only used in this single location. However, when the Rust team tried to replace it, it made the compiler significantly slower. Pretty weird. You can read about it at these links, which of course will be linked in the description. The function gets the size and align of T using the two size and align functions we've already looked at. It calls these two functions and returns their values as a tuple to the caller. So now we have both the size and align of T. Lastly, we call this from usizeAlign unchecked unsafe method. The safety guarantee is upheld because T is instantiated and thus can't have an invalid size or align. Let's see its implementation. It seems to do exactly what the name suggests, creates a layout from a size and an align without any safety checks. As we've seen many times, this macro is only compiled in debug builds. It ensures that align is a power of 2 and that the rounded up allocation size does not exceed isize max. We'll talk about rounded up allocation sizes later. For now, we can brush it to the side. So to create the layout, the size and align are simply inserted into the struct without any checks. The align must be transmuted to the correct type, in this case, alignment. This is guaranteed to be safe because the method itself is unsafe, which means the caller already checked for us. So we return this constructed layout to the caller. The result is returned as T's layout from the layout new method. Layout new has given us T's layout, which is the layout associated constant passed into inner's grow1 method. Here, we stand on the precipice of a large body of code. Let's finally look into how RawVec inner grow1 works. As we know, this method takes a mutable reference to self and T's layout and returns nothing. First, we call this method self.growAmortized and only do something with the result if it's an error variant. That's what this syntax means. If the self.growAmortized method returns an error variant, this code path will execute. Otherwise, the method will end because there's no else block. Okay, let's go one more method deep and check out growAmortized. Note that the arguments are self.cap.0, 1, and T's lm layout. GrowAmortized takes a mutable reference to self, a usize len, a usize additional, and a layout lm layout. The return type is a result composed of unit and try reserve error. First, let's see what try reserve error is. Try reserve error is an error struct with an internal kind, try reserve error kind. Tri-reserve error kind is an enum with two variants: capacity overflow, which indicates that the collection has overflowed its maximum capacity, and alloc error, which is a general memory error that includes information about the layout of the errored memory. These two variants make up the tri-reserve error kind enum that lives inside of the tri-reserve error struct, which is the error variant of the return result of grow amortized. Remember from the last video that the result enum has two variants, OK and err. Result is an important part of Rust error handling because it allows a user to specify two mutually exclusive return values in one type. So grow amortized returns either a unit OK variant or a tri-reserve error variant. This return type is a common API design in Rust. A method that modifies an object often returns a result with unit and an error type. The error is returned if an error occurred during execution, and unit is returned if execution succeeded, but no descriptive information needs to be returned. Thus, OK unit simply means success in this scenario. So the method takes the three parameters we explained and returns either unit or an error. First, another debug assertion that we will ignore. This checks that additional is greater than 0, which is ensured by all calling contexts. Next, we check if t's size is 0, which means that t is a ZST. According to this helpful comment left by the authors, this scenario is only possible if the RawVec is over full. Since this method is only called when the length of the Vec is equal to the capacity of the Vec, and the capacity of any Vec that stores ZSTs is usize max, this would only happen if we made a Vec with usize max ZSTs, which is silly and ridiculous, but Rust protects you anyway. Therefore, we must return an error with the capacity overflow variant of tri-reserve error kind. However, the return type requires a tri-reserve error, not a tri-reserve error kind, so we use this .into method to convert into a tri-reserve error. We get this method from the from trait. Since from tri-reserve error kind is implemented for tri-reserve error, Rust automatically implements into tri-reserve error for tri-reserve error kind, because it's the inverse of from. Just another strength of the robust Rust type system. So the conversion takes place, and we return the capacity overflow error. Next, we get the required cap variable by doing a checked add of additional to len. Remember that len is the current capacity of Vec, and additional is the number of new memory slots needed to grow the buffer. Since we're only adding one element, additional is 1. These checks are unavoidable because we need to make sure that we aren't overflowing the memory capacity of the Vec. We do this by using the checked add method. This method comes from a macro called uint_impl. I'd suggest checking out the macro because it's pretty cool. Of course, it'll be linked in the description. For now, I'll show roughly what it expands to. The method takes self by value and another self RHS and returns an option of self. Option is another important Rust structure similar to result. Option is an enum with two variants, none and some, where none has no value and some has a value. This enum is Rust's solution to the null pointer problem present in many other languages. With this enum, the user can signal to the caller that a type is either nothing or some desired value. The user has to handle both possible cases to continue the program flow. For checked add, we either return the result of adding self and RHS, or nothing in case of an overflow. This comment explains an optimization that the authors used to make this method more efficient. I'll leave the link in the description, and for now, we'll just pretend it's not there. To do a checked add, we first check this intrinsic function, add with overflow. The function returns a tuple of the provided type and a bool. The bool indicates whether the addition overflowed. If the add overflows, the bool is true. Otherwise, it's false. So we check the overflow behavior of the add and get the bool with this .1 accessor. Tuple types can be indexed with .number, so .1 gets us the Boolean overflow indicator. This is wrapped in the intrinsics unlikely function, which hints to the compiler that the Boolean is false. This enables better branch prediction by the CPU. The function takes in a bool b and returns a bool. We expect this to return false most of the time because that's the whole point of the function. If b is false, which we are expecting, the function just returns false. In the unlikely case that b is true though, before returning true, we call this cold path function. The cold path function is another compiler intrinsic. This cold attribute lets the compiler know that this code is a cold execution path. This changes the execution path weights, which disincentivizes predicting this execution path. LLVM is the coolest thing ever. So cold path indicates that a branch is, you guessed it, a cold path. We use this to hint that true is a cold path in the unlikely intrinsic function. Back in checked add, we mark an overflowing add as unlikely to hint that it doesn't happen often. In the unlikely case that there was an overflow, we return none, so the user can handle the overflow how they choose. In the likely case that there was no overflow, we can just return an unchecked add. We know that this unchecked add is safe because we just checked. So checked add adds two U sizes and either returns their non-overflowing sum or none. We do this checked add with len and additional, which is how we decide the amount of memory we need to reserve. We use the OKOR method to handle the option returned by the checked add. This method takes an option self and an err and returns a result. If self is a sum variant, we return an OK variant with the same data. If self is none, we return an error variant containing the supplied error. The method transforms an option into a result. We use OKOR on the checked add to get either an OK with the add's result or an error with a capacity overflow error. The question mark operator is a built-in operator for option and result that either unwraps the OK/sum variant and binds it to a variable or returns the none/error variant. So in this case, if the add overflowed, the method would instantly return an error capacity overflow to the caller. If the add succeeds, the OK will be unwrapped and required cap will be the internal type, usize. That was a very long-winded explanation, but I hope it made sense and you understand just how powerful Rust's error handling system can be. This system has the potential to completely eliminate entire classes of errors because the compiler enforces that both the error scenario and the success scenario are handled. It gives more power to the programmer by giving them better tools to signal potential points of failure in a program. All of this in an efficient language with easy to understand and easy to write syntax. It's no wonder why people love Rust so much. Why haven't you made your Rust debut yet? Get it? Debut? Stream debut by Bjork. Stream the anchor song. Oh my gosh, wait, she's right here to deliver a message.
Hi, this is Bjork. You should learn Rust. It's a good programming language. Subscribe to BehindBlueScreen.
Thank you, Bjork. Moving on, we get the max of two numbers, self.cap.0 times 2 and required cap. Self.cap.0 is the capacity of the Vec. We multiply the capacity by 2 for amortized growth, hence the method name. I'll link more reading on this, but doubling the capacity every time we need to allocate more memory makes the push method more efficient. Technically, O1 amortized. If you don't know anything about big O notation and made it this far into this video, wow, hi, thanks for the support, but also go read about it. It's super important to computer science. I'll link a few resources to get you started. Back to the code. So we pick the max of two numbers, double the current capacity or the required cap we just calculated. Required cap is the current capacity plus the number of elements we intend to add to the Vec. How do we get the max of these two numbers? The max function just takes two t's v1 and v2 and returns the max. The type t must implement the ORD trait. The ORD trait indicates that a type forms a total order. This is a math term that describes the ordering of objects in a set. Types implementing ORD must also implement three other traits, eq, partial ORD, and partial eq, which is a requirement on eq. I won't go into this system of traits because this video is already way too long, but I'd encourage you to check out the documentation and read the linked Wikipedia articles explaining the math behind them, because it's amazing how elegantly Rust translated this system of relationships into a trait hierarchy. ORD requires one method, comp. According to the docs, the method returns an ordering between self and other. They provide some examples for us. A comparison of 5 and 10 will return ordering less. A comparison of 10 and 5 will return ordering greater. And a comparison of 5 and 5 will return ordering equal. So the comp method takes two inputs and returns their ordering. We've already seen it, but let's check out what ordering looks like. Ordering is an enum with 3 variants: less, equal, and greater. These are guaranteed to be -1, 0, and 1 respectively. According to the only source I could find, this makes it easier to implement other comp-style APIs. So ordering is an enum returned by the comp function of the ord trait. The max function requires its arguments to implement this trait. The body of the function calls v1's max function with v2 as an argument. What version of max is this? This is the version of max that comes automatically bundled with the ord trait. This method does the exact same thing as the max function we've been looking at. It takes 2 arguments and returns their max. The body simply calls another function, maxBy, with 3 arguments: self, other, and ord comp. The maxBy function takes in 2 types t and 1 type f and returns a t. F is bound by the fn_once trait, which I briefly explained in the last video. It represents a function that can be called once and only once. The arguments and return type are also specified: 2 reference to t arguments and an ordering return type, which is exactly the method signature of comp. This means that the maxBy function can accept any comparison function with that signature and use it to find the max. Compare, the supplied comparison function, is called in a match statement. If the comparison returns less or equal, the second argument is returned. If the comparison returns greater, the first argument is returned. So the maxBy function uses a custom comparison function to get the max. It's called with the ord comp comparison method in the ord max function, which is the provided max method for ord types. This max method is called in the max function, which compares our 2 capacity possibilities and returns us the max of the 2. We want the greater of double the current capacity and required cap. Next, we get the max between the previous cap value and this min non-zero cap function. It takes the size of t as an argument. The function itself takes a usize size and returns a usize. Based on the name, we can gather that this function is the minimum non-zero capacity for Vec. The comment above explains the behavior: a capacity of 8 for a size of 1 byte, 4 for less than or equal to 1 kibibyte or 1024 bytes, and 1 for large elements so as not to waste memory. The function implements the comment in code. The 3 branches of the if statement mirror the 3 cases described in the comment. So we use this min non-zero cap function to get the minimum non-zero capacity for our type t, and get the greater value between it and cap. Next, we create the variable new layout with the layout array function. We give the function our cap and our lm layout. The layout array function takes a usize cap and a layout lm layout and returns a result with either a layout or a try reserve error. Let's dive in and find out what this function does and how it does it. We start with this call to lm layout's repeat method. This method takes in a reference to a layout and a usize n and returns a result with either a tuple of layout and usize or a layout error. We saw it in the last video, but let's take a quick peek at layout error. Layout error is a ZST struct implementing error. Now we know the error type. The method signature helps us to understand its purpose: to create a new layout representing the input layout repeated n times. First, we create this padded variable with the self.paddToAlign method. This method takes a reference to a layout and returns a new layout. We make new size with the self.size rounded up to custom align method, which we feed self.align. Based on the name, we can infer that this method gives us a size rounded up to the nearest multiple of the align value. Size rounded up to custom align takes a reference to a layout and an alignment and returns a usize. I want to start by explaining this math. Size rounded up equals size plus align minus 1, bitwise and bitwise not align minus 1. Let's show this in binary. Align is always a power of 2, meaning it has exactly 1 bit set. Align minus 1 is 1 less than align, which means that all of the bits below the single 1 bit are set. We don't know size, so we can just use it as a placeholder value. Adding size and align minus 1, we get a few possibilities. This if size is 0, to this if size is 1, and this if size is very large. we know that size plus align minus 1 is somewhere in this range of bit patterns. So align minus 1 is this bit pattern, and its complement is this bit pattern, where all bits including and above the single 1 bit of align are set. Using the bitwise AND operation on size plus align minus 1 and the bitwise NOT of align minus 1, the bottom of the range is 0, the next lowest value is align, and then this is the sequence of included bit patterns, depending on the value of size. Note that all of these bit patterns are multiples of align. Isn't that cool? This formula will give us a size rounded up to the nearest multiple of align. Let's consider some examples. If size is 0 and align is 4, then size rounded up will be 0. This holds for all 0 size types. If size is 3 and align is 4, then size rounded up will be 4. If size is 5, then size rounded up will be 8, which is 2 times 4. If size is 9, then size rounded up will be 12, 3 times 4. If size remains 9, but align becomes 8, size rounded up will be 16, 2 times 8. Increasing size to 17, size rounded up is 24, 3 times 8. Hopefully you get it. The code to do this is pictured here. Align M1 does align minus 1 using unchecked sub, and size rounded up does size plus align M1 using unchecked add, and then uses the ampersand and exclamation point operators to do the bitwise AND and bitwise NOT operations. The comment here explains how we uphold the safety contracts of unchecked sub and unchecked add. First, align is always greater than 0, so align minus 1 can't underflow. Second, size and align minus 1 are both at most I size max, so adding them can't overflow U size. Third, masking by the complement of align minus 1 means that the result is always greater than or equal to the original size. So now we know how to get a size rounded up to the nearest multiple of align. We use this method to get new size, which is now padded to a value that's aligned. Lastly, we return an unchecked construction of a layout from new size and our alignment. So the pad to align method gives us the padded layout that we'll be repeating. This new padded layout has a rounded up size, which means that it's properly aligned. We needed a layout with an aligned size because otherwise our layout array might end up malformed. We use an if-let statement to pattern match the repeat packed method. This method seems to do the actual creation of the repeated layout. This method takes a reference to self and a usize n and returns a result composed of a self and a layout error. We pattern match on a checked mole between self.size and n. This method works like the rest of the checked number methods we've seen, returning the product of the two numbers on success and none on failure. How does checked mole work? It expands from the same uint impl macro into this. It has the same method signature as checked add like we saw before. First, we get this tuple AB using the overflowing mole method. This method has the same signature as the overflowing add function we looked at earlier, returning a tuple of the product and a bool indicating overflow. We get this tuple AB using the intrinsic mole with overflow function. In the arguments, we cast our usizes to actual t, a type provided by the macro definition. On a 64-bit system, the actual t of usize is u64. So we cast our numbers and pass them into mole with overflow, which resembles other intrinsics we've seen. Thank you, compiler. So we perform the mole with overflow, get the product as A and the bool as B, and return them to the caller, casting the product back to a usize. Overflowing mole is called inside of checked mole and assigned to the tuple AB. We use the intrinsics unlikely function here because we don't expect overflow behavior often. In the unlikely case that B is true, the product overflowed and we return none. In the likely case that the product didn't overflow, we return it to the caller. So this method multiplies our two numbers and either returns their product or none. We use this to multiply our size by n to get the size in bytes of our repeated layout. If we get sum, aka the product did not overflow, we use the checked layout from size alignment method with size and self.align. This method creates a layout from a size and alignment, but makes sure that it's valid. Let's see what rules it enforces. The method takes a size and an align and returns a result composed of a layout and a layout error. We check here if size is greater than max size for align. What's max size for align? The method takes an align and returns the max size for that align. According to the safety contract, the maximum possible alignment is isize max plus 1. This means that for a particular align, the max size for that align is isize max plus 1 minus align. We use an unchecked sub here because we know there won't be an underflow and the compiler can optimize bounds checks. So we get the maximum size for align and use it to ensure size isn't too big. If size is too big, we return an layout error to signal that the layout couldn't be safely constructed. Otherwise, we simply construct a layout with the given size and align and return it to the caller. We use this layout constructor when self.size times n doesn't overflow. Otherwise, we return an layout error. So we use the repeat packed method on our padded layout. If the operation returns an OK, we return an OK with a tuple of repeated and padded.size. If the operation returns an error, so do we. Finally, we know how repeat works. It takes a usize n, makes a padded layout, creates a new layout representing n repeated layouts, and returns either a layout error or a tuple of layout and usize. The layout in the tuple represents the entire repeated memory space, and the usize represents the offset between each element of the repeated layout, also called the stride. After repeating the layout cap times, we map the result to get rid of the unnecessary _pad value. The map method takes a result te and maps it into a result ue using a function op. If we feed it an OK variant, it applies op to the value inside. If we feed it an error variant, it just returns the same error. So we map our result with a tuple of layout and usize to a result layout, because we don't need the stride. Last, we use the map error method, which takes a result te and maps it into a result tf, using a function op. Notice that the error type changed this time instead of the OK type. This time, if we feed it an OK variant, it returns the same OK. If we feed it an error, though, it applies op to the value inside. So we use map error to replace the returned error with capacity overflow. This whole expression creates a layout representing the array we're about to allocate. Layout array still returns a result, so we use the question mark operator to immediately bubble up an error and unwrap an OK. Now we have new layout, the layout of our soon-to-be allocated memory. We're getting extremely close to the end. The last variable we create is pointer. To do this, we use the finishGrow function. We give 3 parameters to finishGrow: new layout, self.currentMemory with lmLayout, and a mutable reference to self.alloc. Starting from the inside out, current memory is a RawVec inner method that takes a reference to self and a layout and returns an option of a tuple of non-null u8 and layout. If we're working with a 0 size type or the vec's capacity is 0, we return none. Otherwise, we multiply the size of our type t by vec's capacity. Then, we create a layout using the multiplied size and t's align. Last, we return sum with a tuple of self.pointer and layout. Remember that self.pointer is a unique pointer to u8. This method either returns a pointer to our memory and its layout, or none, depending on whether we've allocated memory yet. We pass self.currentMemory into finishGrow along with new layout and a mutable reference to self.alloc. FinishGrow is where the actual allocation takes place. This is a very important function. It takes in 3 parameters: new layout, current memory, and alloc. It returns a result composed of a non-null pointer to a slice of u8 and try reserve error. First, we call this allocGuard function with our new layout size. AllocGuard takes in a usize alloc size and returns a result of unit and try reserve error. This comment explains what guarantees this function is created to uphold. We don't ever allocate greater than isize max byte size objects, and we don't overflow usize max. However, on 64-bit machines, we don't really need to do anything here because we only need to check for overflow. In code, we check if usize bits is less than 64. This means we are on a system smaller than 64 bits. If we are on a smaller system, we also check if alloc size is greater than isize max. If both of these conditions are true, we return a capacity overflow error. Otherwise, we just return unit. So this function guards the allocator from errors, basically. If there was an error, the question mark operator returns it. Next, let's check out this whole section. If current memory is a sum variant, we enter the first branch. This debug assert only happens in debug mode. It checks that we're working with the same alignment between old and new layouts. We can ignore it. This line hints to the compiler that old layout and new layout have the same align. This can help with optimizations. How does the function hint this to the compiler? Assert unchecked takes in a bool and returns nothing. This check, again, is only used in debug builds, so we'll ignore it. Okay, so internally, assert unchecked calls an intrinsic function called assume. Assume has the same function signature. The body of the function calls unreachable if b is false. The compiler uses this information to assume that b is always true and applies any optimizations it can based on that knowledge. Unreachable is another compiler intrinsic. It calls the unreachable macro, which is a compiler built-in. The compiler will assume that this code is completely unreachable. It's undefined behavior to even call this function. So assume is called by assert unchecked, which hints to the compiler that old layout and new layout have the same align value. After that assertion, we call the alloc.grow method. We pass into it pointer, old layout, and new layout. Pointer is a non-null pointer to the Vec's memory. Old layout is the layout describing the current Vec allocation, and new layout is the layout describing the memory we plan to allocate. Grow is a provided method of the allocator trait. It takes in the three parameters we just described and returns a result composed of a non-null pointer to a slice of U8 and alloc error. Again, this debug assert only runs in debug mode. It ensures that new layout size is greater than or equal to old layout size. We can ignore it. First, we create new pointer using the self.allocate method with new layout. Remember from the last video that allocate is a method that must be implemented by an allocator. It takes a layout, allocates memory, and returns either a non-null pointer to the allocated slice or an alloc error. We use it here to allocate the new memory we need to grow our Vec. The question mark operator again bubbles up any allocation error we encounter. This function, copy non-overlapping, takes in the pointer to our old memory, the pointer to our new memory, and the size of our old memory. Copy non-overlapping is historically called by a different, less descriptive name, memcopy. The function takes three parameters, source, dest, and count. The first thing we can do is get rid of this precondition because again, it only runs in debug builds. It makes sure that the memory ranges don't overlap. We'll get rid of it. An intrinsic function, copy non-overlapping, lives inside of this function. The compiler will handle this functionality for us. After, we call the intrinsic with the same arguments. Now, we have successfully copied the old memory into the new memory. After copying the memory, we can deallocate the old layout now that it's not in use. Deallocate is the other method that an allocator must implement. Now, the old memory is deallocated. The safety contract of copy non-overlapping is upheld because the two memory ranges don't overlap, and the safety contract of deallocate is upheld by the implementation of allocator. Lastly, we return the pointer to the newly allocated memory, and the allocation is finally complete. So we used this grow method because we had already allocated memory and needed to grow our buffer. If there's no current memory, we simply call the allocate method with new layout. A reminder that the allocate method is implemented by allocators. So if no allocation had happened yet, we allocate for the first time instead of grow. The result of the allocation is bound to the variable memory. Finally, we map any memory error to return an alloc error supplied with new layout for more comprehensive error information. We return either the pointer to the new memory or an error. We have officially finished growing our Vec's memory. We bubble up any allocation error and bind the pointer to the new memory to the pointer variable. Next, we set the pointer and the capacity of the RawVec inner using the set, pointer, and cap method. This method takes a mutable reference to RawVec inner, a non-null pointer to a slice of U8 pointer, and a U-size cap. It sets self.pointer to the requested pointer. How do we construct that pointer? The supplied pointer is cast from a slice of U8 pointer to a U8 pointer. Here's the cast method that we've seen before. So we cast the pointer and wrap it in a unique using the from method. This is the implementation of from non-null t for unique t. It just slots it right in there. Now we have set self.pointer to our unique U8 pointer. Self.cap gets set to the provided capacity. The authors of the library have put so much effort into compatibility that they've added a comment explaining what to do if the allocator API ever changes. So we've set the Vec's pointer and capacity to the pointer and cap which we've spent this whole time calculating. Finally, we return OKUnit, signaling that the function executed without a hiccup. That was the grow amortized method. After going through the whole thing, we understand how it grows the memory of Vec by doubling the capacity and allocating a new portion of memory for Vec's elements to reside. We call this method in the RawVec inner grow1 method with our Vec's current capacity, 1 to indicate we are adding one element, and t's layout. If grow amortized returns an error, we call this handle error function supplied with the error. The handle error function takes a try reserve error and returns an exclamation point. This type is called never. The never type means that a computation will never resolve to a value, typically because the program will exit the process without returning something. We handle each try reserve error kind differently. To handle a capacity overflow, we call capacity overflow. This function literally just panics with the message capacity overflow. So we handle a capacity overflow by panicking. To handle an alloc error, we call handle alloc error with the supplied layout. This function is much larger than capacity overflow, but I think we've proven we can handle anything now, 22 pages into this script. Inside handle alloc error, two functions are defined, a const function ct error and a non-const function rt error. The ct error function just panics with the message allocation failed. The rt error function calls another function called rust alloc error handler with the layout size and align as arguments. This function is a special Rust built-in function. The authors call it the magic symbol to call the global alloc error handler. Suffice it to say, I have no clue how it works. We call it in the non-const function rt error. There are two different compilation configurations considered here. If the panic immediate abort feature is enabled, we just use the ct error function. If the feature isn't enabled, we use this const eval select intrinsic to decide which function we want to run. We went over this intrinsic in the last video, but basically it takes in two functions, one const and one non-const, and decides which one to call. So if we don't have panic immediate abort enabled, this function will choose which error handler to call. So handle alloc error has two error handling behaviors to handle an alloc error. Thus, the handle error function handles the allocation errors that may happen during grow amortized inside of RawVec inner grow1. RawVec inner's grow1 method is called inside of RawVec's grow1 method, which is called inside of Vec's push method. Finally, we're back at the top. So close to the end. Let's stick it out. Consider what we've done up to this point. We've made a len variable and checked if that len is equal to capacity. If it is, we grew our memory by doubling our capacity and reallocating new memory for the Vec. All of the growth code that we just looked at only happens when there's no more space in the buffer to store a new element. Let's keep going. Moving on to this unsafe block, we first create a variable end. Self.asMutePointer gets Vec's underlying pointer to its memory. It does this by calling the pointer method on its RawVec buff. This method does the exact same thing, calling the pointer method on its RawVec inner. This pointer method returns the mutable raw pointer to t. The body starts by calling self.nonNull, which is right down here. This method's body casts pointer using this cast method on unique t. The method casts its internal pointer using this cast method on non-null of t. This method gets the underlying pointer by calling asPointer, which just gets the pointer, and casts it from a star mute T to a star mute U. This non-null cast is the cast inside of unique T's cast, turning it from a unique T to a unique U. This cast is then turned into a non-null using the asNonNull pointer method. This is a simple getter method to get the non-null inside unique. So we have a non-null cast to the desired type, unsurprising based on the function name, that we then turn into a raw pointer using asPointer. This gives us a raw mutable pointer to the beginning of our memory. This pointer method is called inside of the RawVec pointer method, which is called inside of the Vec asMute pointer method. Now that we have a pointer to the beginning of Vec's memory, we add len to that pointer to position it at the desired position in our memory. Add takes a pointer and moves it count memory slots. All this code is for debug builds to ensure the add is safe. There are lots of rules when adding to a pointer. We'll ignore it. The add function calls an intrinsic function offset with the pointer and count. The offset intrinsic moves a pointer from one position to another, offsetting it by count. It does this through simple arithmetic, and the compiler does the heavy lifting. So we offset the pointer using the add method to get a pointer to the desired memory where we'll add value. This pointer is called end. We use the write method to write value to end. The write function is another unsafe pointer function. It takes a destination pointer dest and a source value source. Write, like add, has plenty of rules that are only enforced in debug builds. This one makes sure the pointer is aligned and non-null. Let's push it aside. Write redirects to this intrinsic, write via move. The intrinsic writes the value into the pointed to location. Semantically, source is moved into the location pointed to by dest. This comment explains why they chose to use the write via move intrinsic instead of the copy non-overlapping function. Pause to read it if you're interested. So we use the write function to write our value into the location pointed to by end, the end of the Vec. Last but not least, we increase self.len by 1. Finally, we've waded through the depths of Vec push. Let's recap one last time. We check if len is equal to capacity. If it is, we grow our buffer. After growing the buffer, we get a pointer to the end of the Vec. We write our value to that location and add 1 to Vec's len. That's it. See how much work goes into even the most inconspicuous methods? When I work with a Vec, I just picture some items in a line. Meanwhile, all of that work had to be done to push a single value. In main, we push 0 to our Vec. In memory, Vec is composed of 3 usize values, a pointer, a capacity, and a len. Here's a little demonstration of what our main function looks like in memory. This is very simplified, if you couldn't tell. We create v1 using Vec new. First, we push 0. The Vec begins with no memory allocated, its pointer dangling at 4. Then, we push. 4 slots become available as the capacity becomes 4. 1 slot is filled with 0 as the length becomes 1, and the pointer points to the beginning of the buffer. I'm using a question mark to represent the memory location because the allocator chooses where to allocate the memory, so its value can basically be anything. After pushing 0, we push 1. The Vec looks like it did before. Now push. 1 fills the second slot and the length is increased to 2. Nothing else changes. Speeding up, we push 2. The Vec is the same. Push. 2 fills the third slot and the length becomes 3. Next, we push 3. Vec is the same. Push. 3 occupies the fourth spot and the length is 4. After pushing 3, we push 4. Oh no! The Vec is out of allocated memory. How is it going to fit 4? We're doomed! Just kidding. We just went through the entire code. I had you for a second. The Vec allocates new memory at the last minute, copies the old elements over to its new buffer, deallocates the old buffer, and the capacity becomes 8. 4 is written to the 5th slot and the length becomes 5, the pointer becomes a new unknown memory location, one that could store 8 elements in a row without overlapping other allocated memory. Thus is the behavior of the elusive Vec. 4 has been pushed, and the Vec has been tamed. Go forth with this knowledge and do something with it. I don't know what, but I believe in you. You are so talented and amazing, and if you watched this entire video, I love you. Truly. I cannot believe anyone would stick it out through this whole thing. You're an absolute G. Maybe I'll make a Discord or something for this channel. Stay tuned. Episode 2 coming soon, methinks. Alright, that's it for today. Thank you for watching. This has been Behind Blue Screen. Be kind, and goodbye.